so I'm probably gonna start now. Is that okay for everyone? Okay. Today, this is a presentation made by team, okay. So this is a presentation by Webb Robotics, team 1466, about composite materials, their use in FRC, and more just in general information about them. So just to get us off, I'm going to start just with the basics, what composites are. Composites is a type of material science focused on materials that combine properties of two different materials to make a stronger one. And the materials that it's made from, these are in two categories. It's your matrix and your reinforcement. Reinforcement materials those are like your carbon fibers, your Kevlars, your fiberglass, things like that. Those are man-made, but you can also have natural fibers that you use as a reinforcement material, like hemp, they can be used. These provide strength and stiffness to your matrix, which in a lot of cases tends to be epoxy resin, it can be other resins. But what the matrix does is allow better load transfer and protects the reinforcement materials. Here's some composite materials. This helps explain something you saw on the way in. Lots of desks, we put Rice Krispie treats out on the desk just as a little treat. It's a composite material due to the composite matrix holding the marshmallow matrix holding the rice puffs together and strengthening them, whereas the marshmallow is given structure by the rice. Wood is plant fibers and cells held together by lignin, a naturally decaying polymer. It's similar to resin in how it's used in the wood structure itself. It can actually be replaced by different types of resin to make clear wood. It's a neat experiment to do. Concrete has a cement matrix around the fiber reinforcement of rebar, which helps the cement not crumble due to tensile load. And then carbon fiber is a traditional composite, actually made of a fiber reinforced polymer. So we have started this project with the SAMPE Foundation. It's a 2-year project to develop material science and composite education for FRC teams. That's what this is mainly surrounding. We want to increase the use and prevalence of composite materials like carbon fiber in robot designs and use. We received the grant in summer 2020. It focuses on composites carbon fiber. And eventually it'll turn into lessons and activity texts for teams to use to learn and develop their own uses for composites within their teams. So just to start off on why you should use composites. Well-designed composite materials hold several advantages, like a strength to base ratio. Carbon fiber is better at that than stone. They have great tensile strength, and they have strong resistance to the elements. They won't corrode, they won't rust, things like that. Composites are lightweight, very strong, and can often withstand the stress and force of test robotics when you use them how they're supposed to be used. So just to give a brief overview on where you might want to use composites, they're good high load parts. They're strong and light with things like a telescoping arm, which in one of our years we did make a carbon fiber telescoping arm. This is a cross section cut out of it. Since it's lightweight, it's not as much torque on the robot as it's moving, so it will less force on it because it's lighter weight, so it won't snap or things like that, like a metal arm might. So yeah, things like telescoping arms, extenders, climbers, they are good places for carbon fibers as they are stronger than the plastic parts and lighter than the metal parts. They'll exert less force over what they're attached to, like the motors or any superstructure, and they'll be at a minimal loss of strength compared to aluminum. So there's just some more details on fiber reinforcement. Fibers have lots of variety. Well, lots of carbon fiber parts look similar due to things like the materials used, carbon fiber versus Kevlar, how long each individual piece of fiber is, how they are weaved together and how thick it is. That will change details about your fiber. And fibers are divided into categories based off what they're made of. Glass, carbon, boron, ceramic, metal, Kevlar, natural, and asbestos. Those are all fibers people can and have used. Reinforcements, like resins, those are all going to have different properties and use cases compared to each other, like strength, weight, and tensile strength. But for reinforcement, you need to be careful because they're all skin irritants. Like epoxy resin is a contact irritant, so if you repeatedly come into contact with it, you will develop an allergy to it. So I'm just going to go through the types of fibers that can be used. This is, first off, aramid fibers, otherwise known as Kevlar. They have really strong resistance against impact and abrasion and a low compressive strength. However, it's very hard to machine and work with. This is a piece my team made recently as a demo piece out of Kevlar. Having worked on it, I can tell you it was very hard to actually machine it into the shapes we needed to get it to form around this 3D printed mold. While it's incredibly light and strong and steady, Kevlar was hard to work with doing it. Next, you have carbon fiber. It has a great strength and stiffness ratio compared to its weight. It's very light and very strong. You can see this is a flat panel people on the team have made. It's light, it's strong, nice and steady. But carbon fiber tends to be more expensive than your other options. Next up is fiberglass, otherwise just known as glass. It's used in many things. You see it in bathtubs, boats, and lots of applications. It's lightweight, moderate tensile, compressive strength. It's going to be your cheapest fiber option, and it's very easy to work with. It also has high permeability, so your your matrix will flow into it better and spread out easier. So here on the desk, I have some of the different fiber types. Right here, these are your glass. These are what your fiberglass is going to look with before you add the matrix. These are just reinforcements. So I have a few different types of fiberglass and a few different types of carbon fiber. I'm going to pass these around for people to look at them. Just pass them back up. Go pass those out. So as people are looking at those, I'm just going to keep going with the presentation. So your reinforcement material is going to have some terminology you're going to see looking at it. So let me start with toe. That's the amount of filaments of fiber in a line. You'll see how it's woven together. Your toe determines how wide that's going to be, the weave. The crimp is the bending point where it's woven together. It's where it goes over, under another piece of toe. Stability is the ability for the fiber to maintain the angle it's woven at. You'll see some of them are woven at 45, others are woven at 90. Those have different effects on the straight, and the stability is how it can actually maintain by positioning. The weave, as I mentioned, is just how the orientations of the fiber can be like a 45 or a 90, and then that's just how they are woven together. So weave has lots of effects on the reinforcement material outside of just what the material is itself. Properties can be altered or enhanced depending on the weave. So just the pattern can affect how strong it is and things like that. It changes certain aspects of the closet, how they're constructed. It can affect load or tensile strength, how it moves the force around the whole object, and how it lowers the strength over it. So here are some common weave patterns. I've passed a few around, so if you have them, look at those visible up here too. These are your common weave patterns. And that's just your regular over-under. That's a trill weave. That's a harness satin weave, and then that's a unidirectional weave. They all have different things they're good at and different uses. So yeah, I'm passing the weaves around. I'll go back to the image just so you can see. This one is your standard weave. It has good stability, good orientation, really great at making flat parts and simple shapes. But when you start to get more into rounded shapes and rounded geometry, it struggles because it doesn't move as well. This is called a trill weave. It's in a pattern. The pattern is like 2x2 or 4x4 because that represents how many it goes over, then back under. So this one is a 2x2 because it goes over 2, then under 2. More pieces of toe. This one has decent stability, and it's also decently good at forming around more complex geometries, rounded shapes, things like that. This is a harness satin weave. It's going to have fairly low stability, but it's really good at getting into those hard to reach corners if you're pulling it over a mold, just because it flows much easier. It's named after the actual fabric satin. So, and then last up, you have a unidirectional weave. That one is interesting because it's not woven together at all, so it doesn't have to worry about crimp angles or things like that. Did you pass the unidirectional on it? Okay. If you, whoever has the unidirectional piece, can you hold it up? You'll see that it has some reinforcement things woven into it. All the carbon fiber is still in the same direction, but has some other things holding it together until you can make your part out of it. I have some pieces right here. This one's unidirectional. It's nice and stiff. It doesn't bend very easily, as opposed to this piece, which is your standard weave, which bends much easier compared to it. It has a much higher stiffness and about the same weight. Now to go into more detail about the polymer matrix, that's the other part of your composite material. There are several different types of polymers, with epoxy being the best at several categories. Epoxy is going to have your best strength, shelf life, and it's going to have your lowest weight. So for FRC, it's probably the best thing to use. But it's one of the more expensive ones, and is very sensitive as it's being set. Vinyl ester and polyester resins are also alternatives, each having their own uses and weaknesses. Like, they're not going to have as good a shelf life, or they're going to yellow really easily, or they're going to get mess up other rubber. Resins are skin and eye irritants, so you must wear safety glasses and gloves. And then you want to work in a well-ventilated area because it's going to release a lot of fumes as it's curing. So here's just some more stuff about epoxy resin. It's often seen as the best for composites because it has the best strength and lowest weight out of the common options. It's going to have a bit higher cost, and epoxy resin you need to be careful with. It's a two-part resin, so you're going to have your activator and you're going to have the resin itself. So you have to make sure you have the right ratio for however much you want to use. And it's exothermic, which is a safety hazard. And since it's a two-part, it needs a specific hardness, and sometimes it may use heat to cure, most times it's going to be exothermic. But it's going to have a long shelf life, so you can get a lot of it and then just have it for a while, use as you need. Okay, so vacuum infusion is a common way to make a carbon fiber part. What vacuum infusion does, this is good for making flat pieces. You put your carbon fiber, okay, there it is. Yeah, okay. Let me show you a few pieces. These pieces were both made by the vacuum infusion process. Okay. Pass them around to you. It's a dry laminate, so you get a dry reinforcement material, dry fiber, and then you put that into a mold or vacuum bag, and then the vacuum is poured on it. What vacuum infusion process is special though, you don't put any resin on it until the vacuum's poured, where you then suck the resin into the mold, where it spreads out through the laminate and then back out. Traditional layups are done. A layup is when you're making your piece, that's what it's called as you're getting ready to vacuum form it or make the mold. A wet layup, that's the traditional one. It's where you put epoxy on each layer. It's where you put your resin on each part of the fiber as you put it onto the mold on each sheet. Whereas the vacuum infusion, you have dry fiber until the vacuum's pulled. So there's some just things on a relation for FRC, just some small things as a note recently. As I understand it, with new rules regarding off-the-shelf parts and things like that, if you make a carbon fiber sheet in the off-season, you are allowed to bring it into the FRC game season, which is very good because these can take some time to set up and make properly. So if you have it in the off-season, you can take it into the game season, as I understand the new rules. And then many examples, if you look at FRC teams, look at Chief Delphi, see what they're saying. Many of them will use just stock sheets, flat parts like those, and machine them into what they need. You with them?
Yeah. So looking around on what it says Chief Delphi, there's just a lot of misinformation about how dangerous it is to handle carbon fiber and other composites, which it's not super high risk as long as you're following proper precautions. So obviously safety is always going to be highest priority, but the main risk with these is if you're sawing them or grinding them, because the dust can be very abrasive and harmful to breathe in. And then also, sharp edges have a risk. So, but with proper handling procedures with these, you can almost entirely lower those risks. So, oh yeah, also you can use the ACE cutting
I
edge.
can talk about that.
Yeah, I can talk about that real quick.
So ACE, it's this online learning platform you can use. They are, I believe Oak Ridge did some stuff for the machining classes, like they had CAD, CNC classes and things like that. They have a week-long, fully digital and free composites rep class. It's a great resource to start and explore the topic. It's free, I think it takes a week, 4 hours of course rec, and then it gives you a certification upon completion. I believe that's a QR code for it. If anyone's interested, you can just go ahead and scan that. Okay. Did everyone who wants that get it? Okay.
So-
Do you think that could?
So one of the main, most important things is making sure that you're operating in a very well ventilated environment, because there are fumes that come from the different kinds of resin that can be somewhat harmful. And they're not extremely toxic, but you do need to make sure that you're not breathing them in at high concentrations. So working in either outside or in a very well ventilated room or just an area with a large fan can help lower those risks. And then also PPE is like the main way that you can protect yourself physically. So you'll want to use dust masks to prevent inhaling some of those irritants. And then eye protection, again, for particles. And then gloves are very important because all of these tend to be contact irritants. Wearing gloves will help minimize those risks, and it will help lower any irritation or discomfort that could arise from working with these. And then also disposal is something that you need to be sure to take care of, because resin, especially these two-part resins, are very toxic to just dispose of in their liquid form. So if you're ever working with these, you need to ensure that they are all fully solid, and you need to mix up any of the rest of your resin before you dispose of it, because it's very toxic to wildlife in the ocean, and depending on how you dispose of it. So, here's some examples.
Alright, here's just some FRC examples we found of common fiber pieces. Team 4087, I believe that is Voodoo Voltage, used common fiber in their climate. It's kind of hard to see from these photos, but you can see the CAD of it right there. So that's one place for common fibers being used in the climate. Good weight, it's lightweight, very strong, so that's a good place for it. 7042, I'm not quite sure what team the name is, but they had a few examples. They use it on the 2022 robot, as I believe, on the back of that shooter right there. I think that's how they move the ball around as part of the indexer. And then they used, I believe, a flat plate on it on the 2024 robot on the back of the shooter, as you can kind of see right there. That's Team 33. They had a carbon fiber elevator for 2019. You can see it right there, some facts about it. 84-inch range, 2-stage elevator with 3D printed rollers and things like that. This was a great use of carbon fiber. It's nice, lightweight, moves easily, nice and strong. And then 2767. What is it? Oh, yes. So as you see, him pointing to right there, they use carbon fiber for this elevator right here. So like telescoping arm right here. It will just move up and down with the arm. Oh, sorry, no, I don't have this one. They use the carbon fiber. They use a carbon fiber rod for the arm right here because it's gonna exert a lot of torque because it's swinging far out of the robot. So they use carbon fiber there because of its strength and weight ratio. So it won't snap, things like that for the arm. Okay, those are the last examples I have photos of. I can also tell you about a bit more carbon fiber examples. We used a prefabricated carbon fiber roller on our robot this year. It was in our indexer because we found it had the right friction we were looking for, but it's not too much, not too bad to index the note into our shooter. I don't think we have an example of it. Actually, sorry.
Oh, wait.
Yeah. So we did not make this carbon fiber part, it's just a prefabricated one, but we found it fit our uses. So we machined it into what we needed for our robot, which is, like I said earlier, for the uses in FRC, that's just a very common thing teams will do. Yeah. Do I have any questions? Anything anyone else wants to know about carbon fiber? Sure.
Have you 3D printed in carbon fiber reinforced?
We haven't, I know some teams did have, I think HBA has, that's kind of a different thing, because instead of being your fiber that's laid out in the matrices, one's like chopped up pieces of carbon fiber added to it. I think it increases the strength, I don't know much about it though, because it's, for the most part, relatively different. Any other questions?
Are there any concerns with like machining carbon fiber?
You need to be a little careful. You need to be careful machining it, because like you said, the things of carbon fiber, all the fibers and stuff, once it gets out, they can be very abrasive, similar working with fiberglass, just plain fiberglass, or asbestos, things like that. But for machining it, you also need to be careful with it, because it can be brittle and things like that. So if you're drilling through it, you might want to use like a drill bit that was made for glass specifically, instead of just like a regular drill bit. You need to be careful about things like that, because it's also gonna have a bit of flex. It's not gonna be like perfectly rigid, things like, so you need to be careful of things like that. Any other questions?
Is there a specific source that you guys use to get the prefabricated part?
For prefabricated pieces, I don't believe there's a specific, I don't know if there's a specific source, I need to ask my mentor. But I believe it was probably an FRC vendor. Although for things like flat panels, we tend to make most of those ourselves. We just got the well prefabricated.
Did you do any testing on, like, break a piece and compare it to something else, like another material like aluminum or something you would use?
We haven't done any testing ourselves, but we will have sand after evidence, but it's wet, it's wet about
There's a lot of data out there, I just didn't know
Yeah.
if you all had done any testing.
No, not
yourselves
ourselves.
to see.
What we did do though, in 2023, we did end up making a carbon fiber piece, but it had a core material, so what that is, it's two pieces of carbon fiber, put around a thing in the middle. No, the core material. So you can see this was just put around a honeycomb material. Right here, it's two sheets of carbon fiber around the honeycomb. We ended up trying to do something similar for a 2023 intake, where it's two claws with carbon fiber and then foam as a core material. We did end up snapping one of them. Just that's something to watch out for, because it just depends on the stress you're putting on your carbon fiber. It's great if you're pulling against it like this or compressing it, but twisting it, it doesn't handle the best, at least in a flat sheet like that. So that was just the wrong strain being put on it to utilize its functionality.
So, one of the sheets that you guys passed around, what's like an approximate time that it took to fabricate that?
These sheets we got from a supplier, so I don't know. For the most part though, we don't make the sheets ourselves. We get the fiber as it is, and then we make the solid composite part out of it.
It takes like 4 hours.
Yeah. Depending on your experience stuff, we hosted a workshop where we made, I think, 4 panels like this, just in a lab, just see, get some experience working for ourselves. Took like 4 hours to get everything set up and then start the curing, and then like cure overnight to get the pieces. So if you're interested in time or things like that, that's how long it took for us. But we also have a mentor who is very experienced with composites. To go back to your question about the testing, well, we haven't done any really scientific testing. If you would like to come up here, you can compare the strength to weight versus like flexibility of aluminum and these two carbon fiber pieces on this rig we made. So you can see here, the aluminum bends very easily on it, and it's not as light as these pieces, whereas the unidirectional carbon fiber piece is much stiffer than the aluminum and lighter too. This one is similar to the aluminum and flexible, but flexibility though.
You know, can you mix like different types of fibers within one sheet?
We have haven't done it, I believe you can. So I believe if you want to do like fiberglass and then carbon fiber, I think you could. I'm not sure the benefits that would bring though.
Do you know, like, the factor of how much lighter carbon fiber is to aluminum for its strength?
I do not know off the top of my head, I'm sorry.
So when you're making like a, say, a thicker sheet, is there an advantage of stacking different weaves on top of each other, or is it just better to use one weave throughout?
When stacking sheets like that, we tend to just use one weave, but we rotate it, so that way, as the force is being applied, it doesn't share the same weakness in every direction. So if you stack it all in one direction, then if it has a weakness, all layers are going to have that weakness. But if you offset it by like 90 degrees or 180 degrees, that weakness is going to be spread out instead of just in one area. I assume a similar thing would happen if you used different weaves. But for the most part, I know one of the reasons why we do it. We have a big roll of standard weave, and we cut the sheets off of it. So it's just, since we have so much of it, it's more convenient to cut each sheet out of the same weave. That puts us at 9:55, about just a few minutes early. Anything else? Anything else anybody wants to know?
Thank you.